We can see billions of stars, yet most of them will forever remain beyond human reach. The universe is expanding faster than we can travel, and physics itself has set the ultimate boundary for exploration. There is a boundary surrounding humanity. You cannot see it, you cannot feel it, yet it exists all the same. In every direction, roughly 16 billion light-years out, there is a limit we will never pass. Physicists have calculated, down to the last decimal, how far humans can ever travel into space. And the answer is deeply unsettling. Our telescopes can observe nearly 94% of the universe. We will never physically reach any of it. Space itself is expanding, dragging galaxies away from us faster than we could ever pursue them. And that is only the beginning of the problem. If this reshapes how you think about our place in the cosmos, subscribe and continue this journey with us. Right now, every form of human space travel depends on chemical rockets. Every spacecraft ever launched, every moon mission, every probe sent beyond Earth, all rely on the same basic principle: burn fuel, expel mass, move forward. It is essentially a controlled explosion. The physics behind it dates back to the 17th century. Over time, we refined the design, improved efficiency, optimized every variable. And still, it is hopelessly insufficient for reaching the stars. Think about a car for a moment. Fill the tank, and maybe you can drive 400 miles. Now imagine needing enough fuel to reach the nearest star. Your fuel tank would need to be larger than the Earth itself. The rocket equation shows no mercy. For every additional pound of spacecraft, the fuel requirement grows exponentially. Double the fuel, and your speed barely improves. Triple it, and the benefit shrinks even more. The math collapses into impossibility almost immediately. Consider the space shuttle, one of the most sophisticated machines humans ever built. At launch, it weighed around 2,000 tons. Almost all of that mass was fuel. The shuttle itself weighed just 78 tons. All that fuel lifted it into low Earth orbit, about 250 miles up, roughly the distance between New York and Boston. Meanwhile, the nearest star lies 25 trillion miles away. The scale mismatch becomes obvious. Scientists tested every chemical fuel combination imaginable. Liquid hydrogen and oxygen offer the absolute best performance possible. That same propulsion system carried Apollo astronauts to the moon. Those rockets reached speeds near 25,000 miles per hour. It sounds impressive until you do the math. At that velocity, a journey to Proxima Centauri would take more than 100,000 years. Longer than recorded human history. Longer than humans have had language. NASA engineers understand these limits intimately. They have run the calculations endlessly. Chemical rockets cannot overcome this barrier. The energy density is too low. The mass ratios are unforgiving. It is like trying to cross an ocean in a wooden rowboat, except the ocean is empty space, and it stretches beyond comprehension. And then things become even stranger. Even if the fuel problem vanished overnight, even if we invented a perfect, weightless, infinite propellant, we would still face something far worse. A barrier that makes rocket engineering look trivial by comparison. The universe itself is pushing back, and this obstacle is indifferent to human ingenuity. On December 24th, 2024, a spacecraft called the Parker Solar Probe shattered the speed record for any human-made object, 364,000 miles per hour. Fast enough to orbit Earth in under 4 minutes. Fast enough to reach the Moon in less than 40 minutes. Fast enough to cross the solar system in months rather than years. It sounds like science fiction. It is not. NASA tracking stations across 3 continents confirmed it. Parker achieved this speed by falling toward the sun, stealing momentum from gravity like a slingshot. 7 times it plunged close to the solar surface. Each pass added velocity. Each loop pushed it closer to the absolute limit. Engineers celebrated, and they deserve to. Parker Solar Probe represents the peak of what our current technology can achieve. No human-made object has gone faster, and none will. Using gravity assists and chemical propulsion, we have reached the ceiling. Now consider what that record actually means. Proxima Centauri is 4.2 light-years away, 25 trillion miles. At Parker's maximum speed, the trip would take 7,000 years. 7,000. Roughly 280 generations would pass before arrival. Those descendants would not remember Earth. They would not remember you. Their language would be unrecognizable. Their culture would feel alien. The math is unforgiving and final. Even our greatest speed achievement is laughably slow on cosmic scales. It is like sprinting at full speed only to discover you must cross an ocean. That is our reality. Every physicist working on this problem knows it. Speed records are meaningless when distances are measured in light years, and speed is only part of the problem. Parker Solar Probe carries no humans, no air, no water, no food, no life support. It is just instruments wrapped in a heat shield. Scale that design up to carry people, and the velocity collapses. Mass always destroys speed. A human-rated spacecraft would weigh thousands of tons. Food supplies, water recycling, radiation shielding, living space, medical systems. Every kilogram must be accelerated. The fuel requirements explode beyond what we can build, beyond what physics allows with chemical propulsion. Parker proved something engineers already suspected. We can reach astonishing speeds within our solar system. We can exploit gravity. We can build machines that survive near a star. None of it solves interstellar travel. The difference between what we can do and what we need is not a gap. It is a chasm deeper than space itself. And speed is only the first obstacle. Something else waits between the stars. Something invisible. Something that makes distance look like the easy part. 7 months. That is how long it takes to reach Mars with today's propulsion. 7 months, inside a metal cylinder, barely larger than a small house. 7 months, breathing recycled air. 7 months with the same few people. 7 months knowing that a single mechanical failure could end everything. NASA calls this a Mars transit window. Astronauts use very different words. This is not like traveling to another city. You cannot turn back. Once the trajectory is set, you are committed. Earth and Mars move at different speeds. Launch windows open only once every 26 months. Miss it, and you could drift past Mars entirely. Timing must be perfect. Navigation must be flawless. One error, and the spacecraft becomes a drifting tomb. Engineers built redundancy into every system. Oxygen generation, water recycling, temperature regulation, communications, food storage, medical supplies, waste processing. Every critical function has backups layered on top of backups. And still, systems fail. A ground experiment known as Mars 500 Inches, Russia revealed the psychological cost. After 500 days in isolation, relationships fractured. Communication broke down. Minor disagreements turned into lasting conflicts. And that was on Earth, where help was always just outside the door. Out there in space, there is no rescue coming, no emergency turnaround, no backup you can call for. Once the hatch closes, the crew is alone in a way humanity has never truly experienced. Early missions to Mars will push psychological limits even harder than physical ones. Can people remain mentally stable for 7 months inside a confined shell? Can they cooperate under unrelenting pressure? Can they live with the constant awareness that nothing but thin metal separates them from absolute nothingness? Radiation makes the situation far worse. Mars has no global magnetic field like Earth. The spacecraft has none either. Cosmic radiation slices through the hull as if it were paper. Every day spent in transit raises cancer risk. Every solar flare carries the threat of acute radiation poisoning. Astronauts aboard the International Space Station receive partial protection from Earth's magnetic shield. Crews headed to Mars receive none at all. SpaceX argues that improved propulsion could shorten the journey to 5 months, maybe even 4 under ideal conditions. That helps, but it does not fix the underlying issue. Mars is close. It is practically next door on a cosmic scale. If 7 months is enough to strain human endurance, what happens when the trip lasts decades? What happens when the destination lies light years away instead of light minutes? Mars is a test run, a proof of concept for journeys far longer than anything we have attempted. If humans cannot withstand 7 months to Mars, the stars are permanently out of reach. Engineers understand this. They analyze every malfunction, every breakdown, every psychological failure. They are learning what humans can tolerate. So far, the conclusion is unsettling. We are fragile. We are exposed. We are barely capable of reaching our nearest planetary neighbor. And what comes next makes the Mars journey look like a weekend camping trip. Space is not empty. Between planets, between stars, even in the seemingly calm vacuum near Earth, particles race at velocities approaching the speed of light. We call them cosmic rays. They are not rays at all. They are atomic nuclei, stripped bare protons, helium nuclei, iron atoms hurtling through space at 90% the speed of light. They carry energy levels that feel almost forbidden by nature itself. When these particles strike human tissue, they do not merely damage cells. They tear DNA apart. They trigger cascading chemical reactions. They punch through cell walls and erase genetic instructions refined over billions of years. A single relativistic iron nucleus can slice through 30 cells in a straight line, each cell left irreparably damaged, each impact increasing the probability of cancer. On Earth, we rarely think about this. Our planet's magnetic field deflects most cosmic radiation before it reaches the surface. The particles that slip through collide with the atmosphere, dumping their energy harmlessly. What reaches the ground is only a shadow of the original threat. We live inside a protective cocoon we did not design and barely comprehend. Step beyond it, and the radiation wall reveals itself. Astronauts aboard the International Space Station receive 10 times more radiation than people on Earth. Their missions are capped at 6 months. Even then, their lifetime cancer risk rises by 3%. 3% for half a year. Now scale that to decades. Scale it to interstellar travel. The numbers become lethal very quickly. NASA scientists measured radiation exposure during the Curiosity rover's journey to Mars, 253 days in transit. The accumulated dose equaled 660 chest X-rays. That was for an unshielded robot. A human on the same trajectory would face serious medical consequences. Double the exposure for a return trip, and you approach the career radiation limits imposed by space agencies. Limits specifically designed to keep cancer risk below 3%. Cross them, and you are no longer exploring. You are gambling with your life. Galactic cosmic rays are even more dangerous than solar radiation. Solar flares eject particles, but they are relatively predictable. With enough mass, we can shield against them. Galactic cosmic rays come from far beyond our solar system. They are the debris of supernovas, exploding stars that release more energy in seconds than our sun will emit across its entire lifetime. That energy accelerates particles to absurd velocities. Those particles have traveled through space for millions of years. They remain deadly when they arrive. Shielding against them borders on impossible. Add metal to a spacecraft, and something counterintuitive happens. The incoming particles strike the shielding and generate secondary radiation. Sometimes, that secondary radiation is even more harmful than the original impact. Aluminum, the primary material used in spacecraft construction, performs especially poorly. It produces showers of secondary particles. Polyethylene works better, but effective shielding would require walls several feet thick. The mass quickly becomes unmanageable. The spacecraft becomes too heavy to launch. Experiments uncovered something even more alarming. Cosmic radiation does not only increase cancer risk, it damages the brain. Mice exposed to simulated cosmic rays showed memory loss, impaired decision-making, and cognitive decline. Neurons were destroyed. Inflammation spread through brain tissue. Humans on long missions could arrive mentally compromised. They might forget their purpose. They might not be capable of completing the mission at all. There is no solution yet. Every proposed fix collapses under its own limitations. Magnetic shielding demands enormous power. Water shielding adds prohibitive mass. Faster ships shorten exposure time, but require propulsion systems we cannot build. We are cornered. A radiation wall stands between us and the stars, and we have no way through it. But suppose we overcome it. Suppose shielding finally works. The next barrier is stranger still. Somewhere in the Milky Way, a star 50 times more massive than the Sun is collapsing right now. Its core implodes in less than a second. Temperatures surge to 100 billion degrees. Pressure exceeds anything found in normal matter. The outer layers rebound violently, exploding outward at 30,000 kilometers per second. The light from that explosion will not reach Earth for another 1,000 years. The cosmic rays it created are already here. Supernovas are the most violent events in the universe. In 10 seconds, they release more energy than our sun will generate in 10 billion years. That energy must go somewhere. It accelerates matter, protons, neutrons, iron, and nickel nuclei to relativistic speeds. These particles spread through the galaxy near the speed of light. They travel for millions of years. They do not slow down. They do not stop. Scientists confirmed this reality in 1962. High-altitude balloon experiments detected cosmic rays striking Earth's atmosphere. The measured energies were staggering. Individual particles carried the kinetic energy of a baseball thrown at 60 miles per hour. A single atomic nucleus moving so fast that time itself slowed down from its perspective. The source was traced back to supernova remnants. Our galaxy experiences roughly 3 supernovas per century. Each one sends out a new, expanding wave of cosmic radiation. Earth sits inside overlapping shells from explosions that occurred 10 million years ago, 20 million, 50 million. The Milky Way is saturated with radiation layers. There is no safe corridor between them, no gap. Every cubic meter of interstellar space is flooded with high-energy particles. The radiation that reaches Earth is already dangerous. Our magnetic field blocks most of it. What penetrates is weakened. In interstellar space, there is no such shield. Particles strike at full force. A spacecraft traveling between stars would move through the harshest radiation environment imaginable. The crew would face particle energies that exist nowhere else in nature. And some cosmic rays are stranger still. Ultra-high energy cosmic rays carry energies that push physics to its breaking point. Single particles arrive with more kinetic energy than a professional tennis serve. No one knows how this is possible. Our equations fail. Supernova remnants cannot account for them. Something larger must be involved. Entire galaxies, supermassive black holes are tearing stars apart, colliding neutron stars. The sources remain theoretical. The particles themselves are not. Detectors around the world register them regularly. These extreme particles are rare. On Earth, one strikes each square kilometer of atmosphere roughly once per century. That sounds reassuring until you think about interstellar travel. A spacecraft traveling for decades cuts through trillions of cubic kilometers of space. Over that distance, rarity becomes inevitability. The odds approach certainty. One particle punching through the hull, one particle striking a crew member. The result would be immediate and catastrophic. NASA equips every deep space probe with radiation detectors. The data they transmit back is unsettling. Radiation levels spike without warning. Some spikes come from solar storms. Others arrive as bursts of galactic cosmic rays. Interstellar space is not calm. It is not stable. It is saturated with hazards we cannot predict and cannot avoid. Charting a safe path through space is like navigating a minefield where the mines are invisible, drifting, and never run out. Biology never evolved for this. Every organism on Earth developed under the shelter of our planet's magnetic field and thick atmosphere. Remove that protection, and cells begin to fail. DNA strands break faster than repair mechanisms can fix them. Mutations accumulate. Cancer rates surge. Organs degrade. We are life forms shaped inside a shield, attempting to survive in a galaxy that offers none. The statistics paint a dark picture. And yet, the next thing explains why Earth is still alive at all. Deep beneath our feet, molten iron flows through vast currents inside the planet. The outer core rotates differently than the inner core. That motion generates something invisible yet essential. A magnetic field extending roughly 37,000 miles into space. A protective bubble we cannot see but cannot exist without. This field bends charged particles away from the planet. Cosmic rays strike it and curve off course. Solar wind particles spiral along magnetic field lines toward the poles, creating auroras instead of cellular damage. The shield is imperfect. Some radiation leaks through, but it blocks nearly 90% of the particles that would otherwise sterilize Earth's surface. Mars lost its magnetic field roughly 3 billion years ago. Its atmosphere was stripped away, its oceans vanished, its surface froze into a barren desert. Earth retained its field. Life endured. Satellites have measured the field in detail. It fluctuates constantly. Solar storms compress it on the day side. On the night side, it stretches into a long magnetic tail. The field is strongest near the poles and weakest near the equator. Astronauts aboard the International Space Station orbit within this magnetic cocoon. Even there, they absorb 10 times more radiation than people on the ground. They are barely inside the shield's reach. Leave Earth orbit, and the protection drops sharply. The Moon has no magnetic field. Apollo astronauts were the first humans to experience deep space radiation directly. They were fortunate. No major solar storms erupted during their missions. One powerful flare could have delivered lethal radiation doses. The crew would not have made it home. NASA understood the danger. They accepted it anyway. Spacecraft bound for Mars exit Earth's magnetosphere completely. The field extends roughly 40,000 miles from Earth's center. Beyond that distance, it fades into nothing. Crews traveling to Mars spend 7 months fully exposed. Every cosmic ray, every solar particle event, every radiation source Earth normally deflects becomes a direct threat. Cancer risk estimates assume ideal shielding. Reality will be harsher. Interstellar vessels would face decades or centuries without magnetic protection. Engineers have proposed generating artificial magnetic fields around spacecraft. The power demands are extreme. Deflecting cosmic rays requires continuous megawatts of energy. Solar panels cannot provide that far from a star. Nuclear reactors could, but mass skyrockets. Every kilogram of reactor fuel reduces payload. Every kilogram of shielding displaces food, water, and supplies. Some researchers suggested timing missions during periods of solar maximum. When our star is most active, the solar wind strengthens. It temporarily pushes galactic cosmic rays away from the inner solar system. The effect exists, but it is limited. It helps near the sunday. A few astronomical units out, the protection disappears. This approach might reduce exposure on a Mars mission. It offers nothing for interstellar travel. The magnetic field we take for granted is a planetary miracle. Earth's size is just right, too small, and the core would have solidified billions of years ago. Too large, and gravity would alter the field entirely. Rotation rate matters. Composition matters. Everything must align perfectly. Only one planet in our solar system achieved the right combination. Only one world supports complex surface life. Leaving that shield means accepting radiation levels evolution never prepared us for. It means believing technology can replace billions of years of planetary defense. It means trusting that engineering can solve the same problem that destroyed Mars. The optimism of engineers is impressive. The laws of physics are merciless. We are only beginning to understand the scale of the challenge. And even if shielding were perfected, even if we recreated Earth's magnetic field around a spacecraft, one limit remains absolute. NASA assigns every astronaut a lifetime radiation dose limit. Exceed it, and you never fly again. The threshold is calculated to keep increased cancer risk below 3%. 3% sounds small. It is not. It means 3 out of every 100 astronauts will develop fatal cancer directly because of radiation exposure. Those odds are considered acceptable. Barely. The limits vary by age and sex. Younger astronauts have more years ahead for cancer to develop, so their limits are lower. Women face stricter limits than men because radiation elevates breast and ovarian cancer risk more than prostate cancer. A 30-year-old woman is allowed roughly 600 millisieverts over her career. A 50-year-old man can tolerate nearly double. These numbers come from decades of data, medical studies, cancer registries, survivor records from Hiroshima and Nagasaki. The science is solid. The limits are not negotiable. 6 months aboard the International Space Station exposes astronauts to around 80 millisieverts, roughly the equivalent of 800 chest X-rays. 2 missions consume a quarter of a career allowance. 3 missions end some careers entirely, not by choice, not by failure, but because the radiation debt has been paid. Now consider Mars. A round trip takes about 18 months. Estimated exposure ranges from 300 to 600 millisieverts, depending on solar activity and shielding quality. A single Mars mission could consume an astronaut's entire career limit. Go once, and you may never fly again. The damage is permanent. The mutations remain. Biology does not reset. Your cancer risk does not disappear when the mission ends. It follows you for the rest of your life. And for interstellar travel, the numbers stop being alarming and become catastrophic. Even with the most advanced shielding concepts we can imagine today, a 10-year mission to another star system would expose the crew to radiation doses measured in thousands of millisieverts, far beyond any career limit, far beyond anything considered survivable. The crew would be accepting near certain cancer, probable early death, radiation levels comparable to those seen only in nuclear catastrophes. Some scientists have suggested raising the limits for deep space missions. Let astronauts volunteer. Let them knowingly accept higher risks. Let informed consent replace safety standards. The ethics quickly become uncomfortable. Can someone truly consent to a mission that will almost certainly kill them? Is it exploration if the outcome is death? Or is it a suicide mission dressed up as science? Space agencies have answered no. The limits remain, not because radiation suddenly becomes safe below 3%, but because 3% is the line we chose. Cross it, and we are no longer exploring. We are sacrificing people. Radiation damage accumulates. It does not reset. Every day in space adds to the total. Every cosmic ray impact raises the odds. Every solar particle event pushes the number higher. Unlike toxins that the body can sometimes flush out, radiation leaves permanent scars. DNA does not repair perfectly. Mutations persist. The cancer clock starts ticking and never stops. Studies of Apollo astronauts revealed something troubling. Those who traveled beyond low Earth orbit show higher rates of cardiovascular disease than astronauts who stayed closer to home. The difference is statistically significant. Deep space radiation appears to damage blood vessels, accelerate plaque buildup, and age the circulatory system faster than normal. The effects last decades. Apollo astronauts are still dying from them. Future medicine might help. Drugs that repair radiation damage. Gene therapies that reverse mutations. Treatments that reset cancer risk. None of these exist yet. Betting on them means betting on breakthroughs that may never arrive. The limits we enforce today are based on present reality, current cancer data, current mortality statistics. Future cures are hope. The numbers we have are facts. Career radiation limits exist because radiation kills slowly, invisibly, and without mercy. They protect astronauts from their own bravery. They prevent suicide missions disguised as exploration. And they force us to confront a hard truth. Some places are too dangerous to reach. Some journeys are simply too long to survive. The stars may be one of them. But physics offers a strange loophole, a way to cheat time itself. Einstein predicted it in 1905. The faster you move, the slower your clock runs compared to the rest of the universe. Not because the clock is malfunctioning, because time itself flows differently at high speed. At everyday velocities, the effect is negligible. A jet flying for 10 hours loses only a few billionths of a second compared to someone on the ground. Meaningless, without atomic clocks. But approach the speed of light and the effect explodes. At 90% light speed, 1 year aboard the ship equals about 2.5 years on Earth. At 99%, 1 year becomes 7. At 99.9%, 1 year stretches into 22. The math is confirmed. Particle accelerators demonstrate it daily. Unstable particles moving near light speed live far longer than they should. Time dilation is real. This creates a bizarre opportunity for interstellar travel. If a spacecraft could reach extreme relativistic speeds, the crew would age slowly while Earth continued normally. A journey that takes centuries from Earth's perspective could feel like decades to the travelers. They would arrive young. Their homeworld would be ancient. Everyone they ever knew would be gone. The paradox deepens. From the crew's perspective, they are not racing through space. The destination is rushing toward them. Distances contract. A 4-year journey to Proxima Centauri could shrink to months of experience time at high enough speeds. Space itself shortens. The universe becomes smaller when you move fast enough. But this is where hope turns cruel. Accelerating to those speeds requires absurd amounts of energy. As velocity increases, so does the spacecraft's relativistic mass. Not its physical mass, but the energy required to push it faster. The closer you get to light speed, the harder acceleration becomes. At 99.9%, the energy requirement approaches infinity. You can never reach 100%. Physics forbids it. Light speed is a wall you can approach endlessly but never cross. Physicists have calculated what it would take to push even a tiny probe to 90% light speed. The energy required equals the total output of the sun for an entire year. Every photon, every joule. Focused on accelerating a single spacecraft, we cannot harness that energy. We do not even have concepts that come close. We struggle to capture a tiny fraction of our star's power. The difference between what we need and what we can do is not a gap. It is an impossibility. Time dilation solves the lifespan problem in theory. Go fast enough, and humans can survive journeys lasting centuries. They would age years, while the universe aged millennia. The physics works perfectly. The engineering does not. We cannot build the engines. We cannot generate the power. We cannot overcome the fundamental limits of propulsion. Relativity adds another layer of strangeness. Time dilation depends on perspective. From Earth's frame, the crew barely ages. From the crew's frame, they age normally, while distances shrink. Both views are correct. Neither is privileged. There is no universal clock. This is not philosophy. It is experimentally verified physics. Astronauts aboard the International Space Station experience a tiny version of this effect. After 6 months in orbit, they age about 7 milliseconds less than people on Earth. Not noticeable, not meaningful, but real. Atomic clocks confirm it. Increase the speed, and the difference grows. At relativistic velocities, it becomes years, decades, centuries. Time dilation is not science fiction. It is measured reality, but using it for interstellar travel demands speeds we cannot reach, propulsion systems we cannot construct, energy sources we cannot access. The universe shows us a loophole, then locks it behind impossible requirements. And even if propulsion were solved, the nearest star reminds us how vast the problem truly is. Proxima Centauri lies 4.24 light-years away, a red dwarf, about 1/7 the size of our Sunday. It hosts at least 2 planets. One orbits in the habitable zone where liquid water might exist. On cosmic scales, Proxima is practically next door. On human scales, it might as well be in another universe. Light takes 4.24 years to travel that distance. Light moves at 671 million miles per hour. Nothing moves faster. A photon leaving Proxima today will not reach Earth until late 2029. That is the universe's absolute speed limit. Now compare that to human technology. The Parker Solar Probe, the fastest object we have ever built, travels at roughly 364,000 miles per hour. At that speed, reaching Proxima would take about 7,050 years, 70 centuries, 280 generations. The launch crew would vanish into myth. Their language would evolve beyond recognition. Their purpose might be forgotten entirely. Engineers have proposed faster ideas: nuclear pulse propulsion, riding the explosions of atomic bombs, theoretical speeds around 3% of light speed. That reduces the journey to roughly 140 years. Still multiple lifetimes. Still beyond anything our life support systems can sustain. The designs exist on paper. They have never been built, never tested. The cost would exceed the global economy. The risks defy calculation. Laser sail systems suggest another path. A colossal laser system constructed in orbit. Vast reflective sails mounted to tiny probes. When the laser fires, it slams into the sail, pushing it forward, accelerating the craft to nearly 10% the speed of light. At that velocity, the trip shrinks to just 42 years suddenly, within the span of a human lifetime. The problem is everything else. The laser array would demand infrastructure that does not yet exist. The energy required would rival the output of entire nations. The sail itself would need exotic materials we are currently unable to produce. And yet here's the unsettling part: the physics checks out. On paper, it works. Of all the ideas we've imagined, this one is the closest to reality. Breakthrough Starshot is pursuing this exact approach. Gram-scale probes equipped with light sails roughly 1 meter wide. A massive ground-based laser array proposed in Chile. Target velocity, 10% light speed. Destination, Proxima Centauri. The project has funding. It has real scientists, real engineers, real hardware studies. If everything goes right, no major failures, no political collapse, no technical dead ends, launch estimates fall somewhere between 20 and 30 years from now. This is not science fiction. This is active research happening today. The probes themselves would be microscopic by spacecraft standards. No crew, no life support, just cameras, sensors, and transmitters. They wouldn't slow down. Slowing down takes more energy than speeding up. Instead, they would scream past Proxima at relativistic speed, snapping images as they go, dumping every bit of data they can transmit back toward Earth. That signal would take 4.2 years to arrive. From launch to first images, scientists would wait roughly 46 years. Most of the people who began the project would be retired. Many would be gone. The commitment stretches across generations. Scaling this concept up for humans breaks everything. Accelerating a gram-scale probe is manageable. Accelerating a 1,000-ton crude vessel is not. The laser power requirements explode trillions of times higher. The sail becomes absurdly large, kilometers across. The mass of the ship fights every attempt to move it, and suddenly you are slammed back into the rocket equation. More mass demands more energy. More energy demands more infrastructure. More infrastructure demands more money. The costs spiral beyond the reach of any economy. Proxima Centauri sits right next door in cosmic terms. It is the closest star, the easiest target. If we cannot reach Proxima with our best ideas, then we cannot reach anything. The galaxy might as well be infinite. Every other star is farther. Every other destination demands more time, more energy, more impossible engineering. Proxima is the test. Proxima is the baseline. And right now we are failing it. That red dwarf will outlive our sun by trillions of years. It will still be burning long after the universe has gone dark and cold. Proxima has time, we do not. Human lives are counted in decades. Missions to other stars stretch across centuries. The math doesn't cooperate. The biology doesn't either. We are organisms evolved for a single planet, attempting to cross interstellar space. And the gap between stars is not just distance, it is time itself. Still, some engineers refuse to give up. They propose something extreme. Picture a spacecraft the size of a city, square miles of interior space, artificial gravity created through rotation, fields of crops growing under artificial suns, water recycling systems designed to operate flawlessly for centuries, a fully sealed, self-sustaining ecosystem encased in metal. This is a generation ship, a vessel built not for one lifetime but for many. The people who launch it know they will never arrive. Their children won't either. Their great-great-grandchildren might. Project Hyperion explored this concept in detail. A recent international design competition attracted teams from around the world. The winning concept, named Chrysalis, stretches 36 miles long and supports a population of 2,400 people. The voyage to Proxima would take 250 years at just 1.5% of light speed. 10 generations of humans would be born, live entire lives, and die in space without ever setting foot on a planet until the end. The challenges are overwhelming. Life support has to be nearly perfect. Water recycling must exceed 98% efficiency. Even small losses compound over centuries. Begin with enough water for 2,000 people. Lose just 2% per year, and you're dry in half a century. Every system needs redundancy. Every backup needs another backup. Every component must be repairable using materials already on board. There are no resupply missions, no rescue, No second chances. Food presents the same nightmare. The ship requires real agriculture, rotating habitats with artificial sunlight. Crops must supply enough calories for the entire population. Waste must cycle back into fertilizer. The ecosystem has to remain balanced forever. One pest outbreak, one fungal infection, one failed harvest. Any of these could cascade into starvation. The ship wouldn't be a vessel anymore. It would be a coffin. Social collapse may be even more dangerous than mechanical failure. Studies of isolated groups show consistent patterns. After roughly 500 days, cohesion begins to break down. Relationships strain. Factions emerge. Conflicts intensify. The Mars 500 experiment, conducted on Earth, with emergency exits just meters away, barely held together. Now stretch that scenario across 250 years. How do you prevent civil war? How do you maintain order among generations who never agreed to this mission? Children born aboard did not volunteer. They inherit confinement with no exit. Genetics becomes a critical constraint. A population of 2,000 is barely sufficient to avoid inbreeding over 10 generations. Population control becomes mandatory. Genetic screening becomes unavoidable. Possibly even arranged reproduction to preserve diversity. The ethics are terrifying. You are engineering a society, controlling reproduction, making choices that would be unthinkable, illegal on Earth. But without them, the population collapses into genetic disorders and infertility. Education becomes another fragile link. Every generation must inherit the full body of knowledge required to keep the ship alive. Engineering, medicine, agriculture, navigation, programming. The transfer has to be flawless. If one generation fails, systems begin to decay. Expertise disappears. Repairs become impossible. There is no tech support, no replacement parts. The crew must be self-sufficient in ways no civilization ever has been. And then there is the psychological weight. Everyone knows they are sacrificing their entire life for a destination they will never see. They are maintaining systems for people who do not yet exist. What gives that life meaning? What stops despair? What prevents suicide? These are not engineering problems. They are existential ones. Some designers suggest virtual reality simulated Earth environments, artificial skies, the illusion of open space. But the psychological impact is unknown. Does VR help? Or does it deepen the pain by reminding people what they've lost? Does it soothe or does it fracture identity? We don't know. And we cannot know without building a generation ship. The risk is too high to experiment. The ship itself would demand a propulsion system far beyond anything humanity has ever constructed. The most serious candidate is nuclear pulse propulsion. The idea is brutally simple. Detonate nuclear bombs behind a massive pusher plate. Let the shock waves slam into the ship. Ride the explosions forward. In theory, this can push a vessel to a few % of light speed. This isn't speculation. Small-scale versions were tested in the 1,960 seconds. Project Orion demonstrated that the physics works. The problem isn't feasibility, it's scale. A city-sized spacecraft would require thousands of nuclear detonations. International treaties explicitly ban this. Politics may be the final wall we cannot cross. The cost is almost impossible to comprehend. A generation ship would be the most expensive structure ever built by humans. Trillions of dollars, decades of construction in orbit. raw materials pulled from multiple nations, entire economies redirected toward a project that will not deliver results for centuries. No government operates on that timeline. No political system survives long enough to see it through. No economy can justify spending generations of wealth on a mission whose success will not be known for hundreds of years. The project would require global cooperation on a scale humanity has never achieved. And even then, after the ship is built, after it launches, success is not guaranteed. Systems can fail, mistakes can compound, the crew can die, and we would not know. There would be no updates, no distress calls, no progress reports, just silence. For centuries, the risk is absolute. The commitment is total. There is no second attempt. But let's assume the impossible. Assume every technical challenge is solved. Assume the ship launches perfectly. The real cost has only begun. 7 people, 14 months, 1 Antarctic research station. By month 6, crew members had stopped speaking to one another. Communication degraded into written notes. Arguments over trivial issues stretched on for days. Depression became universal. This was not a simulation. This was a real mission in Antarctica, with rescue theoretically available. They still nearly collapsed. Psychologists study isolation because space agencies need answers. How long can humans tolerate confinement? Where is the breaking point? The data is unsettling. Submarine crews on 90-day patrols show measurable increases in aggression and anxiety. Prisoners placed in solitary confinement suffer permanent psychological damage within weeks. Astronauts aboard the International Space Station are limited to roughly 6-month missions, partly due to mental health concerns. Beyond that threshold, the risks rise sharply. The problem isn't just isolation, it's sameness. Every day looks identical. The same walls, the same faces, the same meals, the same routines. Human brains evolved for variation, for novelty, movement, changing environments. Remove that, and cognition degrades, motivation erodes, depression takes hold. Studies show that even watching recordings of forests, oceans, and wildlife reduces stress in confined subjects. Now imagine decades without ever seeing a tree. No rivers, no birds, just metal corridors and recycled air forever. Social structure adds another layer of danger. Every group forms hierarchies. Power consolidates. Leadership is contested. In normal life, people escape unhealthy situations. They move, they quit, they walk away. On a spacecraft, escape does not exist. You are locked in with the same individuals for years or lifetimes. Personality conflicts become inescapable. There is no divorce, no resignation, no distance. Research on confined populations reveals predictable patterns. After initial bonding, factions emerge. In-groups and out-groups harden. Minor disagreements evolve into permanent divisions. The Mars 500 experiment illustrated this clearly. Russian and European crew members stopped collaborating. They ate separately. They worked independently. The mission barely remained operational. Add real danger and total isolation, and the breakdown would be worse. Sleep disruption compounds everything. Spacecraft lack natural day-night cycles. Artificial lighting attempts to simulate circadian rhythms, but imperfectly. Astronauts aboard the ISS report chronic sleep disorders. Sleeping medication becomes routine. Fatigue accumulates. Judgment deteriorates. Reaction times slow. The crew becomes less capable precisely when competence matters most. Communication delays introduce yet another psychological burden. Messages between Earth and Mars can take 20 minutes one way. Real conversation becomes impossible. You send a question and wait 40 minutes for a reply. The interaction feels hollow, detached. Now extend that to interstellar distances. A message sent to a ship near Proxima takes over 4 years to arrive. The response takes another 4 years. Conversations stretch across 8 years. The crew is effectively alone. Earth cannot assist during emergencies. It cannot offer guidance. It cannot provide emotional support. The isolation is complete. Some psychologists suggest carefully selecting crew members with specific traits: low need for social novelty, high tolerance for monotony, strong introversion, exceptional self-regulation. This creates an ethical dilemma. Are you selecting astronauts or engineering a specialized subset of humanity? Are you choosing people or shaping them? Over generations, selection pressure could fundamentally alter the crew's psychology. The humans who arrive may not resemble the humans who left. Virtual reality is often proposed as a solution. Simulated Earth environments, artificial skies, digital oceans. But the risks are real. Crew members may prefer the simulation to reality. Addiction becomes possible. People retreat inward. Social bonds weaken. The ship still requires labor. Systems still need maintenance. If the crew disengages mentally, the mission fails. VR is a tool, but it can also become poison. Medication is another proposed solution. Antidepressants, anti-anxiety drugs, mood stabilizers, chemical balance through pharmacology. The ethics are troubling. Are you treating illness or chemically enforcing compliance? And what happens when supplies run out? Pharmaceuticals do not last centuries. Complex drugs cannot be produced without an industrial chemical base. Maintaining synthesis capability introduces yet another fragile system, another failure point. Collapse may not come violently. No mutiny, no catastrophe, just gradual decay. Motivation fades. Maintenance slips. Errors accumulate. Systems deteriorate. The ship dies slowly from neglect. By the time anyone realizes what's happening, recovery is impossible. The mission fails quietly, predictably, inevitably. But the mind is only half the problem. The body faces something even more unforgiving. Every rocket carries a brutal truth in its fuel tanks. The more mass you carry, the more fuel you need. The more fuel you add, the heavier you become. This feedback loop, the tyranny of the rocket equation, destroys most spacecraft designs before they ever leave paper. Konstantin Tsiolkovsky identified this problem in 1897. The math has not changed. The limits are absolute. Launch 1 ton into low Earth orbit, and you need roughly 30 tons of rocket at liftoff, a 30-to-1 ratio. Now, scale that to interstellar travel. Send a 1,000-ton ship toward Proxima at just 1% of light speed, and the fuel mass becomes astronomical. Millions of tons. Billions. The numbers explode beyond any feasible construction scenario. Chemical propulsion simply cannot do this. For interstellar travel, it isn't inefficient. It is impossible. Liquid hydrogen and liquid oxygen represent the absolute peak of chemical rocket performance. There is nothing better in that category. Their exhaust velocity reaches roughly 4,500 meters per second. That sounds impressive until you do the math. To reach just 1% of the speed of light, a chemical rocket would require a mass ratio exceeding 9 trillion to 1. That means 9 trillion kilograms of fuel for every single kilogram of payload. More mass than Mount Everest. The spacecraft would collapse under its own weight long before ignition. Nuclear propulsion improves the situation, but not nearly enough. Nuclear thermal rockets using uranium fuel can double exhaust velocity to around 9,000 meters per second. That cuts the mass ratio dramatically to about 2 million to 1. Still impossible. 2 million tons of fuel for every ton of spacecraft. At that point, the vehicle becomes nothing but fuel with a microscopic payload compartment. There is no room for humans, no room for life support, no room for shielding, no room for anything that makes survival possible. Fusion propulsion looks better on paper. Hydrogen fusion releases extraordinary energy. In theory, exhaust velocities could reach 30,000 meters per second or more. That brings the mass ratio down to roughly 4,000 to 1. Still enormous, but now, at least, mathematically survivable. The problem is reality. We have never built a fusion rocket. We have barely sustained fusion reactions for seconds in laboratory experiments. Constructing a fusion engine that operates reliably for decades in space belongs firmly in science fiction. The technology does not exist. No timeline exists for when it might. Project Daedalus, designed in the 1,970 seconds, explored this idea seriously. It proposed a fusion-powered probe to Barnard's star using deuterium-helium-3 fusion. Target speed, 12% of light. The launch mass, 54,000 tons. Of that, nearly 50,000 tons was fuel. The payload was almost negligible. The mission assumed mining helium-3 from Jupiter's atmosphere. We have never attempted that. We do not know if it is feasible. The entire design rests on technologies we cannot demonstrate. Antimatter propulsion represents the theoretical ideal. Matter and antimatter annihilation converts mass directly into energy with near-perfect efficiency. Exhaust velocities approach the speed of light. Mass ratios fall into ranges like 10 to 1 or 20 to 1 numbers that actually look reasonable. But antimatter is the ultimate bottleneck. Producing a single gram requires staggering energy. Current production rates are measured in nanograms per year. An interstellar mission would require tons. The energy cost would exceed the total output of human civilization for centuries. Some engineers suggested harvesting fuel during flight. The Bussard ramjet concept uses enormous magnetic fields to scoop hydrogen from interstellar space and fuse it for propulsion. In theory, the spacecraft never runs out of fuel. The mass ratio becomes irrelevant. The idea collapses under scrutiny. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter. To collect enough fuel, the scoop would need to span thousands of kilometers. The magnetic drag would likely exceed the thrust produced. Most physicists consider the concept unworkable. Beam-powered propulsion offers another route. Build an enormous laser array in the solar system. Focus it onto a reflective sail attached to the spacecraft. Thrust comes from the beam, not onboard fuel. The rocket equation disappears. The spacecraft can be mostly payload. The physics works, the engineering does not. The laser array would cost trillions. The sail would require materials that do not yet exist. Targeting must remain flawless across light years. A fractional misalignment, and the beam misses. The spacecraft drifts into interstellar darkness forever. Every propulsion system encounters the same wall: energy. Moving mass requires energy. Moving it quickly requires vastly more. Accelerating it to relativistic speeds demands energy on a scale we cannot produce. The Sun outputs roughly 400 billion watts continuously. Humanity captures less than a trillionth of 1% of that. The gap between what we have and what we need is not a gap, it is an ocean. Smaller spacecraft help, but only to a point. Reduce payload to 1 ton and the numbers improve. But 1 ton cannot sustain humans. It cannot carry radiation, shielding, life support, redundancy. You can send probes. You cannot send people. That changes the mission entirely. Valuable science, yes, but not human arrival. Not footsteps on alien soil. Launch costs make the problem worse. Every kilogram lifted from Earth costs thousands of dollars. A generation ship weighing millions of tons would cost trillions just to leave the ground. Assembly in orbit would require hundreds of launches over decades. The logistics overwhelm any realistic budget or schedule. The fuel mass problem is not an engineering failure. It is a law of physics. The rocket equation does not care about ambition. It does not care about dreams. It enforces mathematical limits written into reality itself. We can improve efficiency. We can invent better fuels. We cannot escape the equation unless we change the rules entirely. In 1958, physicist Freeman Dyson assembled a group of elite scientists in San Diego. Their task was simple and insane: design a spacecraft powered by nuclear explosions. The project was called Orion. The concept was blunt: detonate atomic bombs behind a massive steel plate. Let the shock waves push the ship forward. Surf nuclear fire. The math worked. The physics checked out. Scale models were built and tested using conventional explosives. They flew. The full design was colossal: 4,000 tons at launch, a pusher plate 130 feet across, built from layered steel and heavy metals. Nuclear pulse units detonated behind the plate every second. Each explosion released energy equivalent to 1 ton of TNT. Shock absorbers smoothed the acceleration. The ship rose to orbit on a pillar of controlled nuclear detonations. Mars in 4 weeks, Jupiter in 8 months, Alpha Centauri in 130 years. This was not a joke. This was funded, serious research. Engineers calculated everything down to the number of bombs required, around 800 nuclear devices just to reach orbit. Thousands more for deep space travel. Every detonation had to be perfect. A failure would turn the spacecraft into a radioactive catastrophe, dispersing fallout across Earth's atmosphere. Environmental concerns ended the project. In 1963, the Partial Nuclear Test Ban Treaty outlawed nuclear explosions in space. Orion was canceled, but the idea never died. Scientists still study it because nuclear propulsion remains the only proven path to high-speed travel within known physics. Chemical rockets are too weak. Fusion is unfinished. Antimatter is unattainable. Nuclear devices already exist. We have thousands of them. We know they work. Using bombs for propulsion sounds insane until you compare it to the alternatives. They are worse. Modern designs refine the concept: smaller nuclear charges, fusion-assisted pellets, magnetic shaping of blast plasma, smoother acceleration, lower radiation, lighter pusher plates. The principle remains unchanged. Controlled nuclear explosions for thrust. Efficiency is extraordinary. Exhaust velocities reach tens of thousands of kilometers per second. Mass ratios become survivable. Payload becomes possible. NASA explored safer variants. Nuclear thermal propulsion uses a reactor to heat hydrogen and expel it for thrust. No explosions, no fallout, just extreme temperatures. The NERVA program, in the 1,960 seconds built and tested functioning engines. Performance doubled chemical rockets. Budget cuts ended the program before flight. The technology exists. We chose not to use it. Nuclear electric propulsion offers another alternative. Instead of using reactors for thrust directly, another approach is to use them for electricity. That electricity powers ion engines. Ion engines are extraordinarily efficient. They produce almost no thrust, but they produce it continuously. The acceleration is gentle, often less than 1,000th of Earth's gravity. You would never feel it, but it never stops. Day after day, month after month, year after year. The spacecraft keeps accelerating, slowly at first, then faster, until the accumulated velocity becomes significant. With nuclear electric propulsion, travel times inside the solar system shrink dramatically. Mars drops from 7 months to around 3. The outer planets become reachable in years instead of decades. Technically, this works. The real problem with nuclear propulsion is not physics. It is perception. The word nuclear carries baggage. Chernobyl, Fukushima, Hiroshima. For the public, nuclear rockets sound like weapons waiting to explode. A launch failure becomes more than a rocket accident. It becomes a radioactive disaster. A vehicle breaking apart during liftoff could scatter radioactive material across large areas. The risk is small, but the consequences are severe. No government wants that responsibility. No space agency wants that liability. One solution is to avoid launching nuclear systems from Earth entirely. Assemble them in orbit. Launch the components separately. Activate the reactor only once the spacecraft is far from Earth, far from any planet. This removes most of the environmental risk, but adds enormous complexity. Orbital construction is slow and expensive. Every component must be launched individually. Assembly requires dozens of spacewalks, robotic systems, and years of coordination. Costs multiply quickly. Then there is radiation shielding. Nuclear reactors emit gamma rays and neutrons. The crew needs protection. Water is one of the best shields we have. Surround the living quarters with water tanks. Meters of thickness, tons upon tons of mass. The spacecraft grows heavier. You gain efficiency from nuclear propulsion and lose it again to shielding requirements. The balance is fragile. Where nuclear systems truly shine is energy density. Nuclear fuel packs enormous power into tiny volumes. Uranium pellets smaller than a fist contain energy equivalent to tons of chemical fuel. A few hundred kilograms could power a spacecraft for decades. No refueling, no resupply. Chemical rockets burn everything in minutes. Nuclear systems run for years. That difference changes everything. But nuclear technology carries political weight. International treaties restrict nuclear materials in space. Weapon proliferation concerns dominate policy. National security agencies get involved. Launching a nuclear spacecraft requires environmental reviews, safety panels, public hearings, years of paperwork. Missions die in committees before metal is ever cut. The irony is clear. The technical problems are solvable. The physics works. The engineering is understood. The obstacles are not scientific. They are political. They are social. We could build nuclear-powered spacecraft today. We choose not to. Fear outweighs ambition. Caution outweighs exploration. And even with nuclear propulsion, there is another idea that changes the picture entirely. Imagine a sail 1,000 feet across, thinner than plastic wrap, made from materials that reflect more than 99.9% of incoming light. Almost no mass at all. This is a light sail. And in theory, it could reach another star system in decades, not centuries, not millennia, decades. The physics is deceptively simple. Light carries momentum. When photons strike a reflective surface, they push it. The force is tiny, almost nothing, but it never stops. Sunlight is free. The sail carries no fuel. It accelerates continuously. In Earth orbit, solar sails work, but slowly. Sunlight is weak at these distances. To get meaningful thrust, the sail must be enormous. Still, the concept works. In 2010, Japan's Icarus mission successfully deployed a solar sail and demonstrated controlled sailing between Earth and Venus. Solar sailing is no longer theoretical. The question is scale. Breakthrough Starshot proposed an answer. Don't rely on sunlight. Use lasers. Build a massive laser array on Earth, likely in the high deserts of Chile. 100 gigawatts of focused light. Aim it at a tiny probe with a sail just 1 meter wide. The laser pushes the sail to 10% of the speed of light in minutes. The probe weighs about 1 gram. The sail is impossibly thin. The acceleration is brutal, tens of thousands of times Earth's gravity. Nothing mechanical survives that. Only a simple chip, cameras, minimal electronics, no moving parts. 10% of light speed means Proxima Centauri in 42 years. The probe does not slow down. Stopping would require more energy than acceleration. It screams past the star system. Cameras fire during the flyby. Data is sent back to Earth. The signal takes another 4.2 years to arrive. Total time, from launch to first images, 46 years. 1 human lifetime. Scientists who start the project could live to see the results. The hardest part is not the probe, it is the laser. 100 gigawatts of perfectly controlled power, a beam miles wide, thousands of synchronized lasers, adaptive optics correcting atmospheric distortion in real time. The physics works. The scale is unprecedented. Estimated cost? $5 to $10 billion. Enormous, but comparable to major particle accelerators or flagship space telescopes. Targeting must be perfect. During acceleration, the laser has to track the probe flawlessly. Any deviation, and the beam slips off the sail. The probe tumbles. The mission ends instantly. The tracking system demands precision beyond anything ever built. Real-time atmospheric correction, artificial intelligence making millisecond decisions. The software alone is a breakthrough. The sail material is another challenge. Reflectivity must be nearly perfect. Any absorbed energy vaporizes the sail instantly. The laser intensity reaches gigawatts per square meter. Ordinary materials would explode. Researchers propose graphene and exotic metamaterials engineered at the atomic scale. Manufacturing them is not yet possible, but progress is steady. Redundancy improves the odds. Launch thousands of probes. Some fail, some drift off course, some are destroyed by micrometeorites. If 10% reach the target, the mission succeeds. The laser is expensive, but once built, it can launch probes continuously. One per week, hundreds per year. Fleets heading toward different stars. Communication is minimal. The probe has no power for a transmitter. Instead, it modulates the reflectivity of its sail, encoding data in reflected laser light. Earth-based telescopes detect the signal. Bandwidth is tiny. Images, telemetry, no video, no real-time communication. Still, it is better than waiting centuries. The flyby limitation is severe. The probe cannot orbit, cannot land. Everything happens in minutes. One chance. After that, it vanishes into interstellar space. A message in a bottle drifting through the galaxy. Scaling this up for humans is impossible. A crewed spacecraft would need a laser array the size of a continent. Power demands exceed global production. The sail becomes absurd. Light sails work for probes. They do not work for people. Some physicists suggest replacing lasers with particle beams, streams of relativistic electrons carrying more momentum than photons. The push is stronger. Acceleration improves. But the fundamental problem remains. Exploration scales. Human transport does not. Theoretically, speeds could reach up to 20% of light. At that velocity, the travel time to Proxima shrinks to roughly 21 years. But the technology behind such speeds remains largely speculative. We understand particle accelerators well. Particle beam propulsion, however, is another matter entirely. The idea exists mostly on paper. Whether it can work in reality is still an open question. Among near-term concepts, Breakthrough Starshot stands out as the most plausible path toward interstellar exploration. Not human crews, not colonization, pure science. Tiny probes, cameras crossing the void to another star within a single human lifetime, sending data back across light years of empty space. Proof that we can physically reach another solar system, even if only with machines. The psychological impact would be staggering. The scientific value impossible to overstate. The first images of an exoplanet's surface. The first direct measurements of another star's environment. The first undeniable confirmation that interstellar travel is not just theory, but something we can actually do. But if we build that technology, we confront one final truth about time itself. Physics sets a hard speed limit. Nothing travels faster than light. 300 million meters per second. 671 million miles per hour. This is not an engineering limitation. It is woven into the fabric of the universe. Photons move at light speed. Anything with mass must go slower. The closer you try to get, the more energy it demands. Infinite energy would be required to close the final gap. You can approach light speed. You can never reach it. Proxima Centauri lies 4.24 light-years away. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers, nearly 6 trillion miles. Multiply that by 4.24, and the result is roughly 25 trillion miles separating us from our nearest stellar neighbor. At light speed, the trip would take 4.24 years. That is the absolute minimum, the theoretical floor, the fastest possible journey, even in principle. Now add reality. Spacecraft do not begin at light speed. They accelerate. Even with perfect propulsion, reaching 90% of light speed takes time. If you could maintain one full gravity of acceleration continuously, you would need about 9 months to reach that velocity. Then you coast. Then you decelerate for another 9 months on arrival. Total travel time, roughly 6 years. Faster than anything we can realistically build. Still completely beyond current technology. Breakthrough Starshot targets 10% of light speed using laser-driven probes. That alone pushes the minimum travel time to 42 years. The probe does not slow down. It screams past the target system at full speed. Including communication delays, the total mission duration stretches to around 46 years. And that assumes perfection. The laser array works flawlessly. The probe survives extreme acceleration. Targeting remains precise across trillions of miles. Nothing fails over decades of flight. Historically, first attempts at new technologies rarely succeed. Failures are likely. Delays are inevitable. Timelines will stretch. Human missions face even harsher limits. People need air, water, food, radiation shielding, medical care, living space. Every requirement adds mass. More mass means lower speed. Propulsion systems scale up. Fuel demands explode. Travel times grow far beyond probe estimates. Even with revolutionary propulsion, a crewed human mission to Proxima would likely take at least a century. Multiple human lifetimes, generation ships, or suspended animation. No quick trips, no weekend voyages. The 40-year minimum applies only if we reach near relativistic speeds. Today's spacecraft are nowhere close. Voyager 1 moves at about 38,000 miles per hour. That is roughly 0.006% of light speed. At that pace, reaching Proxima would take 73,000 years. Chemical propulsion might push us to 0.1% of light speed. That still means a 7,000-year journey. Nuclear pulse propulsion could reach 1 to 3%. That shortens the trip to somewhere between 140 and 420 years, still measured in generations. Time dilation offers no easy escape. Below 50% of light speed, its effects are minimal. At 10%, the dilation factor is just 1.005. Crew and Earth age almost identically. No shortcuts, no tricks. At 90% of light speed, the factor rises to about 2.3. 1 year on board equals 2.3 years on Earth. Noticeable? Yes. Transformative? No. You still age decades during the voyage. Cryogenic suspension could, in theory, let crews skip the journey subjectively, freeze them after launch, thaw them before arrival. But that technology does not exist. Freezing living tissue causes catastrophic damage. Ice crystals shred cells. Current cryonics research focuses on preservation after death, not revival. Safely freezing and reviving humans remains science fiction. Progress continues, but no guarantees exist. Missions cannot be planned around technology that has not been proven. Hibernation is more plausible. Bears do it naturally. Metabolism slows. Food and water needs drop. Long periods of sleep reduce psychological stress. Early studies are promising. Modified hibernation could extend supplies and limit confinement fatigue. But hibernation is not freezing. Metabolism continues. Aging continues. A 40-year journey still consumes 40 years of biological time, even if most of it is spent unconscious. That 40-year minimum to Proxima is aspirational. It assumes technologies we barely understand. Laser arrays not yet built. Propulsion systems not tested. Materials not manufactured. Success rates unknown. Realistic timelines are longer, much longer. Early missions will rely on conservative, proven designs. That means centuries, not decades. And Proxima is the closest star. Barnard's star lies 6 light-years away. Sirius, 8.6. Wolf, 359. Nearly 8. Nearby stars cluster within 10 to 20 light-years. Even at 10% of light speed, these journeys span 1 to 2 centuries. The galaxy itself stretches across 100,000 light-years. We struggle to imagine reaching our nearest neighbors. Everything beyond them may as well be unreachable. Time is the ultimate barrier. Not energy, not propulsion, not radiation. Time. Human lifespans are finite. Missions longer than a lifetime demand generation ships or suspension technologies we do not yet possess. The 40-year minimum mocks our ambition. Even that lies beyond our reach. We dream of stars. Physics does not care. The distance between those dreams is measured in years we do not have. So how far have we actually gone? September 5th, 1977. A Titan rocket lifted off from Cape Canaveral carrying a spacecraft the size of a small car. Voyager 1. Its mission? 5 years studying Jupiter and Saturn, then onward into deep space. It carried cameras, particle detectors, magnetometers, and a golden record sounds and images of Earth, a message for any intelligence that might encounter it billions of years from now. Voyager 1 is still alive. 47 years later, it continues transmitting. The signal is faint, 20 watts, less power than a refrigerator light bulb. The radio waves take 22 hours to reach Earth at light speed. NASA listens with enormous antennas. The data arrives. Temperatures, cosmic ray counts, magnetic field readings. The spacecraft is sending information from beyond the solar system. Its current distance, about 14.8 billion miles, 157 astronomical units. An astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Voyager crossed the heliopause, the boundary where the solar wind ends and interstellar space begins. It entered territory no human-made object had ever reached before, and yet it is barely beyond our cosmic doorstep. Proxima Centauri is 25 trillion miles away. Voyager has covered just 0.06% of that distance in nearly half a century. At its current speed, it would take 73,000 years to reach our nearest star. Even then, Voyager is not headed toward Proxima. It is traveling toward a star known as AC+, 79 degrees, 3,888. It will pass within 1.6 light-years of that star in about 40,000 years. 40 millennia. 800 generations. The spacecraft will outlive human civilization. Eventually, its electronics will fail. Voyager is powered by a radioisotope thermoelectric generator. Plutonium-238 decays, producing heat. Thermocouples convert that heat into electricity. The isotope has an 87-year half-life. Power output drops steadily. NASA began shutting down instruments in 2019. Cameras off, heaters off. Only essential systems remain. By around 2030, power will fall too low to operate any instruments. Voyager will fall silent, but it will keep moving. The structure itself is durable. Aluminum and titanium frame. Gold-plated copper electronics. The golden record protected beneath an aluminum cover. Cosmic rays degrade materials slowly. Micrometeorites erode surfaces. Over millions of years, the spacecraft will fade into debris, a cloud of particles drifting through interstellar space. For now, it remains intact, a functioning machine in the void. Voyager travels at 38,000 miles per hour relative to the Sunday, about 17 kilometers per second. It sounds fast. On cosmic scales, it is nothing. Light travels at 186,000 miles per second. Voyager moves at roughly 0.0006% of that speed. The comparison is humbling. Our fastest machine is unimaginably slow, a snail crossing a continent. The distances involved are staggering. 2 identical spacecraft were launched decades ago. Voyager 2 lifted off 16 days before Voyager 1. Different trajectories, different targets. Voyager 2 visited Uranus and Neptune, the only spacecraft to ever reach those planets. Today, both Voyagers travel through interstellar space. Voyager 2 sits about 12 billion miles from Earth, just behind its twin. Both continue in separate directions, carrying their golden records. Silent ambassadors of a species that might no longer exist before they ever reach anything. Their lifespans depend entirely on power. Without electricity, the spacecraft cannot transmit. Antennas cannot point at Earth. Instruments cannot function. Mechanically, some systems survive. Momentum wheels keep the spacecraft stable, orientation maintained. But without communication, Voyager is lost. We cannot track it. Data stops flowing. It drifts as another piece of cosmic debris, forgotten, invisible, a ghost of human ambition. Voyager represents the furthest reach of current technology. 47 years of travel, 14 billion miles, just 0.06% of the distance to our nearest star. It proves we can build machines that last for decades in space. We can send signals across billions of miles. We can explore the outer solar system. But the stars? They remain beyond our grasp. The distances are too vast, the speeds too slow, the timescales too long. Future spacecraft could go faster. Nuclear propulsion might multiply Voyager's speed 10 or even 20 times, shortening a journey to Proxima to 3,000 or 4,000 years. Yet even then, it is hopeless for human missions. Still multiple generations, still beyond practical planning. Voyager marks our present boundary, a limit measured in tiny fractions of what we need to travel. But the universe itself imposes boundaries. The Milky Way is not alone. It belongs to a cluster, 54 galaxies bound by gravity. Andromeda, the largest, lies 2.5 million light-years away, hurtling toward us at 70 meters per second. In 4 billion years, the Milky Way and Andromeda will collide, merging into one enormous elliptical galaxy. Triangulum is the third major member, with 30 smaller dwarf galaxies orbiting these giants. This is the local group, our cosmic neighborhood, our gravitationally bound family. Beyond the local group, space expands. Galaxies move apart not by flying, but because the space between them grows. The fabric of the universe stretches, carrying galaxies with it. The farther away a galaxy, the faster it recedes. Hubble discovered this in 1929. Decades of observation confirmed it. The universe is expanding, and the expansion accelerates, driven by mysterious dark energy. We cannot see it, cannot measure it directly. We only perceive its effects. Galaxies far enough away recede faster than light. They are not moving through space faster than light. That would break relativity. But the space between us and them grows faster than light can cross it. The light they emit will never reach us. They are beyond the cosmological event horizon. Today, that horizon lies about 18 billion light-years from Earth. Beyond it, galaxies are forever unreachable. We can still see some because their light was emitted when they were closer. That light has been traveling billions of years. The galaxies have since receded beyond the horizon. We see the past. We will never see the future. We cannot visit them. We cannot communicate with them. They are removed from the universe we can ever influence. The local group sits safely within this horizon, roughly 10 million light-years across. Gravity dominates here. Expansion cannot pull it apart. Future civilizations, billions of years from now, will still have this group to explore. Everything else, beyond the horizon, will have vanished from view. This creates a hard ceiling for human expansion. Even with perfect propulsion, even at light speed, our reach cannot exceed the local group. This is the ultimate exploration limit. 18 million light-years may sound vast. It represents only about 6% of the observable universe. 94% of galaxies we can see are already unreachable. The distances grow too fast. Physics forbids contact. Within the local group, billions of stars, trillions of planets, and countless worlds remain enough to occupy civilizations for millions of years. The constraint is not targets, it is time and distance. Andromeda, at 2.5 million light-years away, would take 2.5 million years to reach at light speed. No civilization lasts that long. No species remains unchanged across such spans. Any mission would arrive to find the homeworld extinct. Evolution having moved on, travelers would be the last of their kind. Even nearby galaxies are practically unreachable. The Small Magellanic Cloud, 190,000 light-years away. The Large Magellanic Cloud, 160,000. Both are satellite galaxies of the Milky Way, visible from the southern hemisphere. Beautiful spirals, but still far beyond practical reach. A trip there would consume more than half the entire existence of Homo sapiens, who have existed for roughly 300,000 years. And that is assuming travel at light speed, which we cannot achieve. The cosmological horizon will continue to shrink. Dark energy accelerates the expansion. Distant galaxies will recede beyond reach. Billions of years from now, only the local group will remain visible. All others will vanish, redshifted into nothingness. Future astronomers will witness a small cluster of galaxies surrounded by emptiness, evidence of the wider universe erased by cosmic expansion. This is the ultimate prison. Physics confines us to the local group. No technology can change it. No propulsion, no ambition, no invention can cheat the expansion of space. Draw a sphere, 18 million light-years in radius, around Earth. Everything inside, theoretically reachable. Everything outside, forever beyond reach. This boundary is absolute, final, written into the very mathematics of space-time. 6% of the observable universe. That is our maximum playground. Sounds vast, but compared to the rest, it is incomprehensibly small. Hundreds of billions of galaxies, trillions upon trillions of stars, uncountable planets, all forever unreachable. We can observe them, study their light, measure properties, but never touch, never interact. The local group is not a technical limitation. It is cosmic. Physics drew the line. Expansion enforces it. Nothing humanity invents can cross it. Imagine a wall, invisible, untouchable, uncrossable. It exists not in space, but in space-time itself. This is the cosmological event horizon, the ultimate boundary of everything humanity can ever influence or reach. Today, it sits roughly 16 billion light-years from Earth. Beyond it, we are cut off from the universe forever. The horizon behaves differently than you might imagine. It is not a solid barrier. Spacecraft do not bounce off it. A signal sent toward a galaxy beyond the horizon travels at light speed, but the space between grows faster. The signal never gets closer. It runs on a cosmic treadmill, perpetually accelerating away. Eventually, the message redshifts into nothingness, diluted, stretched, lost. The horizon shrinks. Every second, more of the universe slips beyond our reach. Galaxies that are visible today will eventually vanish beyond the horizon over billions of years. While the observable universe seems to grow as new light reaches us, the portion we could ever explore shrinks relentlessly. Dark energy drives this relentless acceleration. Space expands faster and faster. The horizon moves closer, and we lose access to more of reality with every passing moment. Consider what this means for interstellar travel. A spacecraft launched today toward a galaxy 15 billion light-years away would never arrive. Even at light speed, the galaxy recedes faster than the ship approaches. The journey becomes infinite. Fuel runs out. The crew perishes. The ship drifts forever through expanding space, never reaching its goal. This failure is not mechanical. It is fundamental physics. Observations confirm it. Astronomers study distant Type 1 supernovas, explosions with consistent brightness that act as cosmic yardsticks. Measuring hundreds of these events, they plotted distance against redshift and discovered that the universe's expansion is accelerating, not slowing. This revelation, earning the 2011 Nobel Prize, overturned centuries of expectations. Gravity does pull matter together, but some unknown force is pushing the cosmos apart, and it is winning. The exact location of the cosmological horizon depends on precise cosmological constants: dark energy density, the Hubble parameter, matter density. Scientists measure these, but uncertainties remain. The horizon could be slightly closer or farther than current estimates billions of light-years off. But whether it is 14 or 18 billion light-years away, it remains forever unreachable. This precision matters for cosmology, not exploration. Some have speculated wildly. Manipulate dark energy, alter expansion rates, create regions of modified spacetime with different rules. This is fantasy. We cannot even detect dark energy directly. We only see its effects. Controlling what we cannot observe is impossible. The reality is fixed. The horizon limits information as well. Light from beyond it never reaches us. Nothing beyond that boundary can be observed or studied. For all practical purposes, the universe outside it might as well not exist. We are confined to what we can see and theoretically reach. Everything else is hidden forever. Billions of years from now, the cosmos will appear even bleaker. Only gravitationally bound structures, like our local group, will remain visible. Individual galaxies, everything else will have slipped beyond the horizon. Astronomers of that era will see a small cluster of galaxies surrounded by darkness. No cosmic microwave background, no distant galaxies, no evidence that a larger universe ever existed, all traces erased by expansion. This is the ultimate barrier. The cosmological event horizon is the final word on how far humans can ever explore not what current technology allows, but the absolute physical limit. The boundary is absolute, unchangeable. We are trapped inside it as surely as we are trapped inside time itself. Beyond the horizon, the universe continues, but we are permanently separated. The wall is invisible, but real, forever. And that wall is closing in faster than ever. In 1998, two teams studying distant supernovas reached a shocking conclusion. The universe is not only expanding, it is accelerating. Galaxies are flying apart faster now than billions of years ago. Something invisible, unknown, makes up roughly 70% of the universe's energy density. Scientists called it dark energy, without knowing what it really is. This discovery overturned expectations. Gravity should slow the expansion, like a thrown ball slowing as it rises. Instead, the universe accelerates, like a ball pushed upward by an unseen force. Observations of distant galaxies show their light stretching toward red wavelengths as space expands. The more distant the galaxy, the greater the redshift. The curve of redshift versus distance reveals an ever-increasing acceleration over time. Dark energy behaves unlike matter or radiation. As space expands, matter dilutes. Dark energy stays constant. More space means more dark energy. More dark energy means faster expansion. The cycle amplifies itself. There is no natural break. Look ahead. In 100 billion years, all galaxies outside our local group will have vanished beyond the horizon. Their light stretched to infinite wavelengths, effectively invisible. The sky will be empty, except for the merged remnants of the Milky Way and Andromeda, dark and isolated. Future civilizations will see only a tiny island of matter surrounded by infinite nothing. They will never know what we know now. Some theories predict even worse. If dark energy strengthens, the universe could face a big rip. Expansion would accelerate until galaxy clusters, galaxies, solar systems, planets, even atoms themselves are torn apart. Timescales for this are tens of billions of years, maybe never, but the uncertainty is enormous. We do not understand dark energy enough to predict its behavior. Other models suggest expansion might slow or even reverse. So far, observations show near constant dark energy density over the last few billion years, but we cannot measure the far future. Einstein's cosmological constant may provide a clue. Once dismissed as his biggest blunder, it turns out he might have been right all along. The cosmological constant is energy inherent to empty space itself. Vacuum energy, the restless quantum fluctuations that never cease. It does not dilute, it does not fade. It perfectly explains what we observe, yet we have no idea why it has the value it does. The measured value is staggeringly smaller than what theory predicts by 120 orders of magnitude. It's the worst prediction in the history of physics. Some theories try alternatives, modified gravity, tweaks to general relativity that mimic cosmic acceleration without dark energy. The math can work, but physics has no experimental backing for these ideas. Occam's razor favors the simpler explanation: unknown energy filling space. Strange, but true. This acceleration changes everything. Without it, distant galaxies could eventually be reached given enough time. With it, they slip permanently beyond the horizon, beyond access. The reachable universe shrinks with every second. Technology cannot beat the expansion of space. Even light-speed travel does nothing if the destination is receding faster than light. We are losing access to the cosmos in real time. The philosophical and scientific implications are staggering. We live in a brief cosmic moment when galaxies are still visible. Past eras had different physics, different expansion rates. Future eras will see less. We are lucky to exist now, when evidence of the Big Bang, the cosmic microwave background, ancient galaxies, and quasars is still within sight. This window is closing slowly but inevitably. The universe is hiding itself, one galaxy at a time, and the force doing it, dark energy, makes up 70% of everything we cannot see, cannot measure, and do not understand. We detect dark energy only through its effects: expansion, gravitational lensing, formation of cosmic structures. No particles, no fields, no mechanism, just the undeniable push that separates galaxies. The simplest idea is vacuum energy. Even empty space teems with virtual particle-antiparticle pairs popping in and out of existence, generating energy from nothing. But theoretical calculations overshoot reality catastrophically by 120 orders of magnitude. Why is the vacuum energy so small? We do not know. Decades of research produce more questions than answers. Something fundamental is missing from our understanding. Some propose evolving dark energy fields that change over time: quintessence, phantom energy. Others suggest modifications to gravity at cosmic scales. The math can be constructed, but the physics remains speculative. Observations, however, confirm acceleration. Multiple independent methods, type Ia supernovas, cosmic microwave background, baryon acoustic oscillations, galaxy surveys, all converge on the same conclusion: dark energy is real. The magnitude is staggering. Dark energy dominates 70% of the universe. Dark matter is 25%. Normal matter, the stars, galaxies, planets, gas, and dust, we know makes up just 5%. We live in a cosmos ruled by the unknown. Experiments to detect dark energy directly have failed. It interacts only via gravity. No electromagnetic force, no nuclear interaction. Unlike dark matter, which might someday be detected, dark energy is a property of space itself. We cannot trap it, isolate it, or experiment on it in a lab. The implications for the fate of everything are profound. If dark energy grows stronger, a big rip could tear apart galaxies, stars, planets, even atoms. If it weakens, expansion might slow or reverse, leading to a big crunch. If constant, we face the big freeze. Eternal expansion, darkness, cold, and death. Stars burn out, black holes evaporate, the universe becomes empty and lifeless. No scenario is gentle. All end in obliteration. Now, consider exploration. The observable universe is vast, 93 billion light-years in diameter, containing roughly 4 × 10^80 cubic light-years. Hundreds of billions of galaxies, each with hundreds of billions of stars, countless planets. Yet how much can we ever reach? The cosmological event horizon sits about 16 to 18 billion light-years away. Beyond that, galaxies recede faster than light, forever unreachable. Even within that horizon, the zone we can influence is tiny. Gravitationally bound structures resist expansion. The local group remains accessible, spanning only 18 million light-years. Everything outside our cluster accelerates away, crosses the horizon, and disappears. That tiny fraction, roughly 6% of the universe, is all that we can ever reach. The rest, 94%, we can see through telescopes, but never visit, never send messages to, never touch. Within that 6%, there are about 50 galaxies: the Milky Way, Andromeda, Triangulum, and dozens of dwarfs. Total star count? About 1 trillion. Sounds immense, until you compare it to the universe as a whole. Roughly 200 billion galaxies, 100 billion trillion stars. We have access to 1 in 10 billion stars. The rest? Gone. Lost forever to cosmic expansion. And even that 6% is mostly unreachable practically. Light speed travel to Andromeda, our closest giant neighbor, takes 2.5 million years. No technology, no biological life, no civilization can survive or remain unchanged over that span. Evolution moves faster than that. Any crew that arrives would likely be different from the crew that launched. Assuming survival, assuming the mission even succeeds, millions of years of travel, impossible to maintain, replace, or repair machinery or life support. Focus on what is truly reachable. Our galaxy, the Milky Way. Roughly 100 billion stars, perhaps 400 billion planets. Vast, yes, but infinitesimal compared to the universe. The Milky Way itself stretches 100,000 light-years across. Even traveling at 10% of light speed, it would take 1 million years to traverse. This is our cosmic reality. Expansion, dark energy, finite lifespans, and physics itself conspire to limit human reach. We are children peering into a vast, accelerating, mostly inaccessible universe. Our ambitions, our technology, our species, they matter only within this tiny, shrinking bubble. The rest? Gone. Forever. Crossing the galaxy isn't just difficult, it's effectively impossible for humans. Traveling the full 100,000 light-years takes 1 million years. The far side of the Milky Way might as well not exist. too distant, too slow, too long. Let's narrow it to what's actually reachable within human-relevant timeframes. Assume a spacecraft travels at 10% of light speed. Assume missions under 1,000 years are acceptable for generational crews. Draw a sphere with a radius of 100 light-years around Earth. Everything inside? Potentially explorable. Everything outside? Beyond the lifespan of any civilization. Within that sphere are roughly 14,000 stars. 14,000 out of 100 billion trillion in the observable universe. That's 1 in 7 trillion, 0.000000004%. Most are dim red dwarfs, inhospitable worlds with tidally locked planets. Eternal day on one side, endless night on the other. Extreme temperatures, volatile atmospheres. Only 50 to 100 of these stars resemble our sun-yellow main sequence stars, potential hosts for habitable worlds. 50 stars. That's our entire roster of realistic destinations. The universe shows us a buffet, yet serves us crumbs. Through telescopes, we glimpse galaxies 13 billion light-years away. Spiral structures, dense clusters, exotic phenomena, all forever beyond reach. We are cosmic tourists, peering through a window we can never open. The view is breathtaking. The access? Non-existent. Optimists might argue that 6% of the universe is enough. 1 trillion stars to explore, enough to keep humanity busy for millions of years. True in theory, false in practice. Distances are too vast. Speeds are too slow. Timescales are too long. Even exploring 50 local stars would take thousands of years. The entire local group? Billions. By then, humanity would have evolved beyond recognition or vanished entirely. We can see the universe, but we cannot touch it. Our eyes outrun our hands by billions of light-years. Astronomy developed long before astronautics. We can measure the cosmos long before we can travel it. The gap between observation and exploration doesn't shrink, it widens. Telescopes improve faster than propulsion systems. The universe reveals itself, but slips away simultaneously. 6% is the generous estimate. Realistic access is closer to 0.01%, practically even smaller. We are confined to a cosmic bubble so tiny that calling it a prison feels generous. It's more like a cell, a closet, a box. Outside, infinity stretches in every direction. The universe isn't just unimaginably large, it's fundamentally unreachable. Why can't we escape? Physics itself forbids it. In 1905, Einstein published Special Relativity. Buried in the mathematics was a statement that reshaped everything. Nothing with mass can reach the speed of light. Not difficult, not expensive, impossible. Energy requirements grow toward infinity as velocity approaches light speed. Infinite energy is unavailable. Light speed is unreachable. Not a technical limitation, but a law of reality. Mass and energy are equivalent, E equals mc squared. As an object accelerates, its kinetic energy adds to its relativistic mass. At 90% of light speed, a ship weighs twice its rest mass. At 99%, 7 times. At 99.9%, 22 times. At 100%, mass approaches infinity. Energy required becomes infinite. The wall is built into space-time itself. Massless particles, photons, gluons, maybe gravitons, travel at light speed naturally. No slower, no faster. Add any mass, and the speed limit drops below light. Not one exception, not a loophole. Some physicists imagined exotic solutions. Warp drives contract space in front, expand it behind. Ride a bubble faster than light without moving through normal space. The math works within general relativity. The physics? Impossible. Requires negative mass, exotic energy, more than exists in the visible universe. Wormholes? Tunnels connecting distant points instantly. Step in here, emerge light years away. Mathematically valid? Yes. Physically? No. Keeping a wormhole open requires exotic matter, vast amounts, and we have no way to create or stabilize them. Even if we could, faster-than-light travel brings paradoxes. Time itself breaks. Arrive before you leave. Send messages to the past. Kill your grandfather before your parent is born. The universe seems designed to protect causality. Light speed is a fundamental barrier for a reason. Quantum mechanics offers strange exceptions. Entanglement allows instantaneous correlations across distances, but no usable information travels faster than light. The barrier remains. In short, the universe is vast, beautiful, and accelerating away from us. Our reach is tiny, our journey limited by the laws of physics themselves. We can observe, measure, dream, but crossing the stars? That remains forever beyond our grasp. Einstein once called it spooky action at a distance. Quantum entanglement. Measure one particle, instantly know something about its partner, no matter how far apart. Sounds like faster-than-light communication, but it isn't. No messages, no energy, no shortcuts. Nature teases us with effects that look impossible, but obeys the ultimate speed limit. Scientists imagine tachyons particles, always faster than light. The math allows them. Experiments? Nothing. If they existed, causality would break. The universe would behave differently. Hyperspace? Science fiction. Jump into a higher dimension and cross light years in hours? Fun in stories. Impossible in reality. String theory suggests extra dimensions, but microscopic, inaccessible. Hyperspace is fantasy. Light speed is the cosmic barrier. Not technology, not money, not clever engineering. Space-time itself enforces it. Cause and effect have a speed limit. Information cannot travel faster. This is baked into reality. As fundamental as math, 2 + 2 = 4. Light speed is absolute. Nothing changes it. Particle accelerators slam protons at 99.99999% of light speed. They don't go faster. Energy just makes them heavier. The mass rises. The curve never hits 100%. Cannot reach it. Will never reach it. Billions of experiments, decades of repetition. The law holds. Relentless. Merciless. Humanity is trapped. Stars are light years away. Light speed is unreachable. We can see them, measure them, name them, but cannot touch them. The universe teases us, transparent, gorgeous, yet forbidden. Everything is visible, nothing accessible. Even if we accept physics, biology stands in our way. Consider the grizzly bear, 7 months hibernating, heart rate from 55 to 9 BPM, temperature from 99 degrees to 88 degrees. Metabolism slows to 25%. No food, no water, no urination, no defecation. yet survival is perfect. Spring comes, the bear awakens, fully functional. Evolution solved scarcity. Suspended animation is natural. Scientists sequenced bear genomes. Thousands of genes activate only during hibernation. Muscles preserved, bones maintained, organs protected. The body enters a new state, not sleep, not unconsciousness. A controlled metabolic shift. Months of inactivity, zero damage. Humans carry some of these genes, mostly dormant. NASA explores awakening them. Lower metabolism, slow aging, reduce oxygen, food, water needs. Hibernation could make long interstellar missions mathematically feasible. A 10-year journey? 5 years of supplies if crew sleeps half the time. Suddenly, trips to nearby stars seem possible. But biology is tricky. Cooling humans too fast? Ice crystals form, cells rupture, tissue dies. Medical hypothermia works for hours, not years. Extended stasis may require antifreeze chemicals, pressurized environments, or other tricks to prevent ice. Muscles atrophy in zero gravity. Hibernation could worsen it. Bone density declines without activity. Astronauts on ISS combat this with drugs with partial success. Immune function slows. Infection risk rises. Every factor adds risk. Months stretch into years, years into decades. Even if biology cooperates, time remains a cage. Stars are far. Light speed, unreachable. Voyages measured in centuries, generations. Human civilizations rarely last even thousands of years. Evolution reshapes crew members mid-journey. The species that arrives may be unrecognizable from the species that departed. Technology must last millions of years without maintenance. Impossible. Every day brings new hazards. Radiation, micrometeorites, system failures. Time itself conspires against the travelers. The universe watches, transparent, beautiful, infinite in appearance, yet finite in reach. We see galaxies billions of light years away, yet they remain forever out of touch. Spiral arms, star clusters, black holes, nebulae visible, untouchable. We are cosmic tourists, peering through a window we can never open. Optimists argue we have enough 1 trillion stars in our local bubble, enough to keep humanity busy millions of years. True in theory, false in practice. The distances are staggering, speeds too slow, time unforgiving. Even exploring the 50 most promising stars nearby would take thousands of years. Local group exploration, billions of years. By then, humanity itself would have evolved beyond recognition or vanished entirely. The cruel irony, our eyes outrun our hands. Observation surpasses exploration. Telescopes reveal more than rockets can reach. The gap widens. Every advance in astronomy highlights the chasm. The universe expands, reveals itself, and retreats simultaneously. Reality is far harsher than imagination, and the harshest limits are written in the cosmos itself. Special relativity, published by Einstein in 1905, buried the ultimate truth. Nothing with mass can reach light speed. Not expensive, not hard, not improbable, impossible. Energy required approaches infinity. The barrier is universal. Mass and energy are equivalent. Accelerate, kinetic energy rises. Mass grows. At 90% light speed, a ship weighs twice as much. At 99%, 7 times. At 99.9%, 22 times. At 100%, infinite. Impossible. Even a single electron cannot reach light speed. The limit applies everywhere. No loopholes. Some dream of workarounds. Warp drives. Contract space ahead. Expand behind. Ride a bubble faster than light. Mathematics allow it. Physics? Nightmare. Requires exotic matter with negative energy. Energy demands exceed the entire visible universe. Wormholes? Einstein-Rosen bridges. Step in one end, emerge light years away. Keep it open? Exotic matter again. Create one? No idea. Engineering space-time itself. Manipulating reality. Time travel paradoxes emerge. Kill your grandfather before your parent exists. Nature forbids it. Quantum entanglement? Spooky, yes. Useful for faster than light? No. Hypothetical tachyons? Unseen. Hyperspace? Fiction. All illusions. The barrier remains. Even if physics and engineering cooperated, biology remains. Hibernation is promising. Bears show the way. Gene activation protects muscles, bones, organs. Metabolic suppression works naturally. Humans may mimic it. Long missions could become feasible, but decades of research lie ahead. Ice formation, muscle atrophy, bone loss, immune suppression, all hurdles. Each solution partial, speculative. Combine physics and biology. The verdict is sobering. Stars remain distant. Light speed unreachable. Lifespans too short. Technology fragile. Civilization transient. Time, mass, biology, and the universe itself conspire. We see wonders across billions of light years. We may never touch them. The cosmos is merciless, patient, indifferent, transparent and unreachable, beautiful and cruel. And yet, we look, we measure, we dream.